general relativity, step by step. I've been making heavy use of space-time diagrams, where we can look at events and the relationships between them and so forth. But there's one defect, which is that there's an infinite amount of area to consider here, and I cannot represent the whole of space-time in a nice compact format, and that's a bit of a disadvantage of this way of thinking. What I want is a nice compact way of thinking about the whole of space-time. And so I'm going to talk about these things called Penrose Coordinates, which get around that problem quite nicely. What we want to do is to map an infinite area to a finite area, and in the case of one dimension, we're used to doing this. If you take a function x, then I can map it quite easily to a finite area simply by choosing a function that looks a bit like this. 0 and 1, let's just say. It could be any value. And we make the requirement that f of x has got to be less than or equal to, no, actually strictly less than 1 and strictly positive. And we also require that f dash of x is strictly positive as well. And this is a nice function. And such f in the statistical literature will be called cumulative distribution function. Oops, that's diff. Distribution functions. It's the probability that a random variable is less than any particular value on the x-axis. So these functions quite nicely map an infinite range to a finite range, which is quite a useful and nice thing to do. So what is the Penrose transformation? Well, we've got Penrose coordinates. You normally say u and v, and they're defined in a dead easy way. U plus or minus v equals this function here, f, which I'm leaving open for the moment. I'll show you different choices in a minute, of, let's say, t plus or minus x. So u plus v equals f of t plus x, and u minus v equals f of t minus x. So of course we can transform between them dead easily, because u equals just adding these two, a half f of t plus x, we're adding, plus f of t minus x, and v of course is the other one, a half f of t plus x minus f of t minus x. Dead easy transformation. This is kind of so obvious and so nice and so clever, and yet it was developed quite late in the theory of relativity, and it took a genius like Roger Penrose, British mathematician Roger Penrose, to come up with this. It's a profound insight. Okay, so what do these things look like if we take this transformation where t and x are our regular time and space coordinates? Well, I've got a whole bunch of examples here. The functions I can choose correspond to either the Koshi distribution or a Gaussian distribution, and they look slightly different, or the logistic. Normally you restrict yourself to symmetric density functions, probability density functions. So what do they look like? Well, let's have a look at the Koshi distribution first. Here it is, this is what it looks like. And you can see that what I've got here are black lines here, which corresponds to lines of constant x, and we've got blue lines here, which correspond to lines of constant t, so they're space-like curves. And I've also indicated right in red, right going, right moving null geodesics in this flat space. The diagram is quite well behaved at the in the central region here. The curves cross at right angles and it behaves itself, but of course you're going to expect something to screw up somehow. And in these four corners here, the coordinates get more and more badly behaved. You see they're crossing at a very shallow angle here, which makes life difficult. There's no standard word for the four corners. I've just called it distant past, distant future, far away right and far away left, but different people call them different things. There's a certain amount of unpleasantness at the corners here, which you can get around by using either a logistic transform, which is this one here. See, it looks much nicer at the corners here. Or a Gaussian one, which I think is the standard that you use for flat space. And we've got this beautiful, beautiful property that we've represented the whole of space-time in a finite area, which has got to count for something. Yeah, so I'm going to stop there. Stop.